Okay, so now we will start the topic of systems of ordinary differential equations. It means that we have not one ordinary differential equation to solve, but we will have a interconnected system of ordinary differential equations. So we'll start from two ordinary differential equations, a system consisting of two ordinary differential equations. So systems of ordinary differential equations, solution by Laplace transforms. So up to now we have covered the Laplace transforms. We have found how to find the Laplace transform and how to find the inverse Laplace transforms. So we only need that much type of information, nothing more than that, to solve the system of ordinary differential equations. So what is the system of ordinary differential equations? Maybe I can give an example. The system of ordinary differential equation is, so for example, a second order differential equation is y1 double prime, maybe I change the color, y1 double prime plus y2 prime, and we have their coefficients. So for the time being we are taking these constant coefficients. Okay, so in terms of a1, okay, a2, and then plus a3 y is equal to some value, okay, which is a function of x. Okay, and similarly we can have a second equation a2, sorry, maybe we can say take these coefficients in terms of b. So b1 y double prime plus b2 y2 prime plus b3 y is equal to some other function, maybe g of x. Okay, so this is the system of ordinary differential equation consisting of two equations. So in likewise we can have maybe three equations as well. So we can set up these kind of equations. So how these equations are set up? So for this we take the example of the spring. Okay, spring example. So for example, we have considered the springs example. So there is a vertical spring and then there is a mass on that spring. Okay, so the motion of this mass is represented by one equation. Okay, but instead of, for example, or we can also have another arrangement of springs. So for example, two springs are in parallel and then there is a single mass. So the motion of this mass will be also represented by a single equation. So these type of mass and mass spring systems, they will not constitute a system of ordinary differential equation, because the motion can be represented by just one equation in terms of y of t, because there is only one mass over here. Similarly, if we have the mass are in series, so these were the mass were in parallel. If we have the springs in series, okay, springs in parallel, springs in series, and there is a one mass, so again we can represent this type of mass with one equation. However, if we have two masses, okay, so there is one spring with constant k1 and then a mass, and then along this mass there is another spring and then another mass with m2. So in this case, if this is mass m1, this is mass m2, this is spring with constant k1, this is spring with constant k2. So each of these masses will have their own motions, okay, which may not be independent to each other, but they may have separate pattern. So we can represent the motion of m1 by y1 with respect to t. We can represent the motion of this m2 by y2 with respect to t. So for this type of situation, we can set up the equation, two equations. Okay, so we know that for a single setup, and then there is a undamped, and then there is no driving force, then we can have this kind of equation. So for example, if this is k and then this is m, so m y double prime plus ky is equal to 0. So this is the equation we have set up many times before. So for this type of system, we will need to set up the equations. So for example, for mass m1, so in this case we can see that this the motion of mass m1 will be actually affected by these two springs, k1 and k2. So for example, as if the mass moves, m1 moves downward, so there is a an extension is this spring k1. However, as a result of that, there will be a compression in that spring k2 as well. So therefore, the overall motion of m1 will be affected by these two springs. So the force acting on mass m1 is maybe represented like this. m1 will be there will be an upward force, okay, which will be equal to the k1 times the extension y1. Suppose this one moves by a distance y1, and then for the downward force, so that will be the extension or compression in this spring k2 by y2. Okay, so this k2, the extension of in this spring will be affected by the other spring, so it will be then given by y2 minus y1. Okay, so in this way the equation for m1 can be represented like this. So from just using this basic equation, m1 y1 double prime, and then for in place of k1 we can represent k1 y1 minus k2 into y2 minus y1, okay, equal to 0. So that was for mass m1. Okay. Remember that when we are setting up these equations, our force directions convention is the same as before, because downward forces were positive, upward forces were negative. However, because I have taken these k1 and k2 forces on the same side as m1 and y1 prime, so that's why it appears that I have taken for this upward force as positive. Actually, for the upward force is negative, so it's the same. So for example, I should have written like this: m1 y1 double prime, so k1 y1 upward, so minus k1 y1, and then for downward force k2 y2 minus y1, which is the same as the first equation. Okay, so this is just for some explanation. So similarly for mass m2, so mass m2 is only attached with spring k2. Okay, so therefore m2 y2 prime, and then plus k2 y2 minus y1. So we will take the same extension or compression in the spring as we have taken in the previous case. Okay, so this expression, the extension or compression in the spring is equal to y2 minus y1. The extension or compression in the spring k1 is equal to y1 only. Okay, so that is equal to, over here, that is equal to 0. So m2 y2 prime. So in this way we have set up a set system of two equations. So we can write these equations like this in terms of y1 prime and then y1 y2 these coordinates. So we can arrange these equations like this. M1, first equation, M1 y1 double prime, then y1 term. So y1 terms are 2 k1 minus k1 plus k2. Y1 terms are 2 k1 minus k2. Okay, so from first equation m1 y1 double prime plus k1 y1, if we take y1 as common, so it will be k1 and then k2 y1. Okay, so it was k1 plus k2 y1 and minus k2 y2 is equal to 0. And from the second equation m1, second equation, this is the second equation. From second equation m2 y2 double prime minus k2 y1, so minus k2 y1 and plus k2 y2 plus k2 y2 is equal to 0. So now we can solve these two equations by the Laplace transform. Okay, so for example, as a numerical example, let's take m1 is equal to m2 is equal to 1 kilogram, is equal to 1 kg, and k1, take k1 as let me see. Let's take the value of k1 as 6 and k2 as 4, and also assume that both springs start from the equilibrium position. So their initial displacement is 0, whereas the first spring, the velocity initial velocity is 1, that means downward, and these for the second spring's initial velocity is -1, that is upward. So these are the initial conditions. Okay, so input these values into these equations. So m1 was 1, m1 and m2 are 1, so y1 prime, then it will be y2 double prime, k1 plus k2 is 10, so 10 y1, and minus k2 was 4 y2 is equal to 0, and then it is k2 y1, so this is 4 y1 and then plus 4 y2 is equal to 0. So we have these two equations. Maybe I can call them as equation 1 and equation 2. So we have to solve these equations by the Laplace transforms. So for this we need to take the Laplace transform of the first equation and also the second equation. So for the first equation, this Laplace transform will be s square y1 minus s y1 0 minus y1 prime 0, then plus 10 y1 minus 4 y2 is equal to 0. Okay, so I will continue this clip in the next continue this problem into the next video clip.